Hey, Dr. Clark here with you again. And in this video, we're going to be looking at an example for how to solve a second order differential equation with impulse forcing. Let's take a look. So we've got a damped harmonic oscillator here, impulse forcing happening at time t equals 2. So that's right here. You can see we've got that Dirac delta giving you that impulse force. T minus 2 indicates that it's happening at t equals 2 seconds. And then the 3 just saying that we're going to shift that velocity from wherever it is, adding 3 units to the velocity. Initial position of 1, initial velocity of 0. And it looks to me like it's probably some kind of underdamped harmonic oscillator. So I would kind of expect a solution that looks like e to the minus t sine of t, that kind of thing. And in fact, I think I did work this one out ahead of time, and this is what the solution tends out to be. So what's going to happen, you're going to start at position 1 with slope 0. You can see right there from the initial conditions. And then we're going to be underdamped. So you're going to come down and then start kind of bouncing back and forth. But then at t equals 2, boom, right there, you've got the slope normally would be this, and it's been shifted to that. So we've basically added 3 units to the slope. So the velocity has a discontinuity in it at t equals 2, but the position is continuous. And that's what impulse forcing does for you. So once you've done that, then you're on a new solution, but it's going to continue to sort of oscillate back down to 0 because it's underdamped. Okay. So that's sort of the answer that we're looking for. And let's see if we can actually get there using Laplace transforms now that we know how to actually Laplace right-hand side. Okay, so to do that, let me just cut out the problem here and paste it onto the next slide. Oh, I guess I kept it there. Okay, that's perfect. So let's Laplace transform the whole equation. So we're going to have S L of y prime using our Laplace transform for derivatives minus y prime of 0 plus 2 and then parentheses SL of y minus y of 0 and then plus 10 L of y equals right-hand side. Well, the right-hand side should be the Laplace transform of that Dirac delta function, which we saw in the main idea video is going to be e to the minus, 2s in this case. All right. So y prime of 0 is 0, so that term is going to cancel, but y of 0 is 1, so we will persist with that term equaling 1. Okay, so then we're going to have to take L of y prime, which is going to give us S L of y minus y of 0 this time, and then plus 2s L of y, just multiplying the 2 in. It'll become minus 2 because we're going to multiply 2 by the y of 0, which was 1. So 2 times 1 is 2 in this case. And then plus 10 L of y. And that's going to equal 3 e to the minus 2s. And then y of 0 is 1. So after that, we're going to get s squared plus 2s plus 10. That's the L of y. That's, of course, that's a characteristic equation for this second order differential equation. And then let's see, y of 0 is 1, but it's going to multiply by s. So we're going to have minus s minus 2 equals 3e to the minus 2s. Sorry, 3e to the minus 2s. And so then L of y should equal basically s plus 2 over s squared plus 2s plus 10 plus 3e to the minus 2s times 1 over s squared plus 2s plus 10, just like that. So now we've taken the Laplace transform. And so the only thing we have to do to solve this problem would be to inverse Laplace transform right-hand side. And if we can do that, we'll have our answer. So let me copy this over to the next slide and start there. So the first thing is you'll notice the denominator looks like an irreducible quadratic. So I need to factor that. So L of y, well, not factor it, but I mean, write it in terms of the shift. That's s plus 2. And then this is going to be s plus 1 squared plus 9. So that 10 is really 1 plus 9. And then s squared plus 2s plus 1 is a double root of s plus 1. So that's really just sort of, pulling the 1 out, factoring s squared plus 2s plus 1 into s plus 1 squared, and then you're left with 9. And then you're going to have 3e to the minus 2s. This will, we'll just write this as s plus 1 squared plus 9. And so what are we going to have here? Now, we got to be a little bit careful because we have the s plus 1 in the denominator. So I'm going to write that as s plus 1 over s plus 1 squared plus 9. And then I'm going to have 1 because 1 plus 1 is 2. I had s plus 2, so I'm going to write that as s plus 1 plus 1. All right. And now I've got sort of the same thing happening on top and bottom there. So this thing has the look of s over s squared plus 9, right? That's kind of the look of it. And so that should be coming from cosine of 3t, right? But because I have the s plus 1, that's telling you that it's really coming from basically e to the minus t times cosine of 3t, right? Because the s plus 1, we're using that first translation theorem. We're multiplying by e to the at becomes a shift of s to s plus a in right-hand side. Okay, so this one here, if I erase this work, should really be e to the minus t cosine of 3t. Okay, so this is L of y, but then y of t should be e to the minus 1t cosine of 3t. Okay, now this next one, that one has the constant on top, which makes me think it's going to be a sine. But when you have 9 here, you really need 3 there. So I'm going to sort of multiply by 3 over 3. And so what we're going to get there is we're going to have 1/3. It is shifted over by 1 unit. So it's still going to be e to the minus t, but it's going to be sine of 3t in this case. Okay, so there is those first two terms inversed back. And now we got to do this last one. Okay, so what's going on here? This looks to me like it should be coming from, well, it looks exactly like this. In fact, because I have that 3 there, I could even write the 3 here. And then this exactly looks like e to the minus t sine of 3t, right? That's exactly what it looks like. But don't forget about this e to the minus 2s. So that is the effect of that Dirac delta. And so what's going to happen is when you come back, you're going to be shifted by 2 minutes and then turned on at t equals 2. So the effect of that Dirac delta from our formula from the main idea video for Laplace of Dirac delta. Okay, so what that's going to generate then is e to the minus 1. Now it's going to be t minus 2 times sine of 3 t minus 2. And then we got to turn that on using the what do they call that? The unit step function at t minus 2. Okay. So what happens is, if you just looked at this, you would say, okay, that's e to the minus t sine of 3t, right? But what we get because of that e to the minus 2s is we get that function, but shifted over 2 units and then turned on at t equals 2. So if we go back to the solution right here, you're seeing a sine function turn on, and that shifts the velocity by 3 units. Okay, because sine affects velocity, but not position. If you think about sine has a first derivative, but its position is 0 at t equals 0. In this case, t equals 2 because it's sine of 3t minus 2. Okay, now the common places to make mistakes here are to not shift it. You got to shift all your t's to t minus 2 and you have to multiply by that unit step function. So it doesn't turn on before t equals 2. You want it to turn on at t equals 2. Okay. So hopefully that is helpful for you, seeing one example completely worked out. Okay. And in the next video, I'll do another example so you can see how another problem might get tackled.